I'll introduce you then without further ado. So it's a great pleasure to welcome our third speaker in this morning's session, Romyar Sharifi, who's now wide awake since it's 9 a.m. in California. And he'll be speaking on Eisenstein cocycles and Motivic cohomology.
Thanks so much for invitation. And yeah, I'm sorry for missing the earlier talks. I'll try to watch them on video. Okay, so yeah, so this is the title of my talk. And it's joint with Akshay Venkatesh. Let's see. So, right, so let me state the goal. So the goal is to give a new construction of explicit maps, which I think, well, maybe you've seen before, maybe not, but the explicit map takes a modular symbol in the homology of, or one of them takes a monon symbol in the homology of a modular curve and returns a cup product or a Steinberg symbol of cyclotomic units and cyclotomic units here. I'm not going to be so precise on the first few slides. You'll notice actually these monon symbols don't lie in the groups I've written, but I'm sort of restricting the map. So these maps were constructed by Buziok and independently by this first map by me. And I conjectured that this sort of map pi n is Eisenstein in some sense, which means it factors through a quotient of this homology group by an Eisenstein ideal in a weight 2 Hecke algebra which acts on homology. So how do I make this go away? Okay, so let's see. So a few comments here. Yeah, move to the next slide. I have too many slides, so okay. Right, so you can check that this map pi n is well defined actually simply by computing relations in Milnor K theory. If you have two n units, then their Steinberg symbol has to be 0, and using that fact for certain cyclotomic n units, you can actually show that the map is well defined because the relations among monon symbols which present homology are satisfied sort of under the map. Well, I thought I changed this to conjecture. Anyway, so yeah, so here's the conjecture. And a stronger form would be that, in fact, the resulting map, now here I really mean this map on homology as I've written it. So it's a map from the homology of x1 of n, the fixed part under complex conjugation, to k2 of z mu n, the fixed part under complex conjugation. And you take the quotient by an Eisenstein ideal, and I conjecture that this is an isomorphism. For, you know, I wrote tentative because, you know, there are some things that make this a bit hard to prove, which we'll see in a bit. Okay, so what's known? So originally I actually conjectured this when p divides n and tensored with zp, so on p parts, in which case the k group can be considered as a Galois cohomology group. And Fukaya and Kato proved the first part of this conjecture, that the map is Eisenstein. Yeah, so it can actually be extended to p not dividing n, their method, so long as p doesn't divide the Euler phi function of n. But there's an obstruction in general, so the conjecture is not proved in general. And the second part of the conjecture, they proved a result towards a p-adic version of actually a stronger conjecture than even this, that this map pi n is inverse to another map on certain eigenspaces. So, okay, right. So what do Akshay and I prove? We prove that the map pi n itself is Eisenstein for the Hecke operators which are prime to the level. Okay, so here, so what do I mean by this? Again, maybe I should say it a little more carefully. this TL minus 1 minus L diamond operator L, you can think of as TL minus the coefficient of an equivariant Eisenstein series of weight 2. And so that's an element of an Eisenstein ideal, and the whole Eisenstein ideal is generated by these operators and maybe UL minus 1 for L dividing N. Actually, yeah, so the way so what we do is prove this, that it's Eisenstein for the prime to level operators. And you'll see I'm going to switch the Eisenstein ideal coming up in a little bit, but move on. So let me very briefly review how Fukaya-Kato proceeded. So the map technically is defined on homology relative to cusps which don't lie above the cusp infinity on x naught of n. And these Monin symbols are taken so that C and D are non-zero. So very roughly what happens is they define a map called a zeta map, which sends a pair CD of integers mod n to Steinberg symbol of 2 Siegel units in K2 of Y1n. And these are, right, and then they have a sort of pullback by infinity map, which you have to make sense of. And the pullback by infinity map sort of forgets the power of Q in this Siegel unit and plugs in, 0 for Q. So gives you the cup product of cyclotomic units we're interested in. So some of the composition of the zeta map and evaluation at infinity is the map pi n we're interested in. And right, the point is that the Zn they can show to be Hecke equivariant via regulator computation, but they're doing everything p-adically, so that's already the first lie in this picture. And they're working in cohomology, and actually they're working in H1, but there's a lot of things that are not quite true here. And this map pi infinity is not only Hecke equivariant, it's which doesn't really make sense but it's Eisenstein. It factors through the quotient by the Eisenstein ideal. So the composition of this Hecke equivariant in this Eisenstein map is therefore Eisenstein, and they get their first part of the conjecture. Okay. Yeah, so that's roughly what they do. And here's what Akshay and I do, which is rather different. Okay, so this is a summary of much of the talk, so I'll come back to this in more detail. We construct a Motivic complex. We work in Motivic cohomology. We look at the Q scheme GM squared, on which GL2Z acts on the right on points. We have a complex which gives an exact sequence like this, where these are sort of residue maps. Here you take K2 of the function field, and here you take K1 of the irreducible codimension 1 cycles or divisors, and here you take K0 of the points, close points. Okay, so to this, somehow via this exact sequence to 1 in the copy of Z corresponding to the point 1, 1 on GM squared, we can attach a GL2Z cocycle valued in the quotient of this K2 by the image of this H2. We can sort of, by its sort of this description, we can somehow easily see it's parabolic and Eisenstein. And then what we do is we pull this thing back via a torsion point on GM squared, 1, zeta n, to obtain gamma naught n cocycle valued in a certain quotient of K2 of, that should be square brackets, K2 of Z mu n, which is then Eisenstein for the, at least for the prime to level operators. And the point is that this cocycle becomes a homomorphism on gamma 1n, and then so it gives you a map from homology, which is the map pi n we defined before. So we see it's Eisenstein. Okay, so that's what much of this talk is going to be about. So let me mention that we also construct the zeta maps, but by a similar method, but we do not use the zeta maps that Fukaya and Kato use in proving that pi n is Eisenstein. in improving that pi n is Eisenstein. Okay, so here we have to introduce an auxiliary integer, or actually we introduce an auxiliary prime because that's fine for our purposes. And we construct similarly a cocycle now valued in just K2 of the function field of the universal elliptic curve over y1 n. And we again pull this back by a torsion section, sort of 0 and the canonical section of the universal elliptic curve over the modular curve, to obtain a gamma naught n cocycle valued in H2 of the modular curve, which again becomes a homomorphism on gamma 1 n and again yields the n. And we can show it's Hecke equivariant. In this case, the universal thing is Hecke equivariant for prime to level operators. Okay, so we can verify Hecke equivariance for prime to level operators in this way. So if I have time, I'll talk about that towards the end. Okay, so great. So let me very briefly say something about Motivic cohomology. I'll just describe it in terms of cycle complexes, which works nice for our purposes. So suppose I have a somehow nice scheme of finite type over a field. So block defined cycle complexes. So in the following way, I mean, ZKY, J is the set of pure codimension K cycles in Y cross the J simplex, which meet the faces of the J simplex properly. You have alternating sums of face maps, which give you boundaries in this complex. And then after some re-indexing of the K and the J, you can define Motivic cohomology as homology of this complex. So here it's HIYK is H2K minus I ZK of Y. So here K is greater than or equal to 0, but I could be an integer in general, and it's only conjectural that this is non-zero for negative integers. These are the same Motivic cohomology groups of Voevodsky if Y is smooth and F is perfect. So, and in fact, I think in all the examples I'm going to give, Y is smooth and F is perfect. So this is a perfectly fine definition. Okay, so what properties, I guess it's important, I'll sort of treat this as a black box, but let me mention, I'll give you a list of properties that it satisfies. So we have pullback maps, proper push forward maps. It behaves well with respect to disjoint unions. You get direct sums of cohomology groups. It's A1 invariant in the sense that if I take a direct product with A1, it doesn't change the group. And now the most important ones are sort of maybe H0 of a connected scheme with H0, 0 is a copy of Z, and all the other HI of zeros are 0. If Y is smooth, then H1Y1 is the units on Y, and all the other HI1s are 0. If I is not 1 or 2, for I equal 2, it's the Picard group. So, and HIYK is 0 for all I greater than K plus the dimension of Y. Okay, so I'm not actually going to use them, but they play quite a role in this talk, but they play quite a role in what we do. If you have a closed embedding and it's open complement, you get a Giesen sequence, which is written down there. And maybe more important for what we do, we have cup products, which behave as one would expect. They come from a pullback of sort of external products along the diagonal. And what is HI of what is the Motivic cohomology of a field? So if I have HI spec F of I, so the same I, that is actually the ith Milnor K group of F, and this gives you an isomorphism of rings where cup product structure is transported to the structure given by Steinberg symbols, so the Milnor K ring. And I'll just recall that Milnor K-theory of a field is the same as K-theory of the field in low degree, if I is less than or equal to 2. And I'll be dealing with I less than or equal to 2 mostly, so I won't write the M. Okay, so the main thing is that H11 is the units and H00 is a copy of Z, okay, for us. In H2, you have cup products that go to H22 of units. Okay, so how do we, let me just briefly mention how one way to get this complex. There's something called a Coniveau spectral sequence. So Motivic, so if I let YP denote the irreducible codimension P cycles on Y, and I look at sort of the Motivic cohomology of the spec of the residue field of this X. So there's this convergent right half plane spectral sequence that converges to the Motivic cohomology of Y. So what does this tell you? If you just look, you take n to be 2. So we have such a half spectral sequence for any n at least 0. So let's take n to be 2. And let's look at the row q equal 2 in this E1 page. The row is written down here. And it looks like what I had drawn before for the complex I said was going to occur. So in particular, what you'll get in the middle term is QD cross, and on the right you'll get for each sum end, and on the right you'll get a copy of Z. And because we're in sort of n is 2, we can see that the homology of this complex, if we view it, I want to view it as K2 is in degree 2, the K1s are in degree 1, and the K0s are in degree 0. So I view it homologically. Its ith homology group is the 4 minus ith cohomology group of Y2 for n equal 2 here. So it computes some of the cohomology of Y. It captures the terms in degrees 2, 3, and 4. Okay, so what if Y were GM squared? If Y is GM squared, then it turns out that the cohomology of GM squared vanishes for I greater than 2, which you can see using the A1 equivariance I mentioned on the last slide. So in fact, the homology of this complex lies only on the left. And so it's a right exact sequence and the kernel of the first residue map. So we call the morphisms residue maps because they're residue maps in K-theory. The cohomology is H2 GM squared 2. So the nice thing about GM squared, I said I let matrices, integral matrices act on the right on GM squared, multiplication on the right. That might differ from other conventions, but that's the one we take. So that pulling back by this right multiplication gives you a left action on Motivic cohomology. So in fact, you can see explicitly what this is going to do on coordinates. Right, this is the right action I wrote down here. Okay. Great, so we have this pullback action. So the nice thing is this entire complex is actually equipped with this pullback action. It's a GL2Z, or in fact, this delta equivariant complex where delta is the matrices of non-zero determinant. Okay. So, so we take a very explicit approach to this construction, and I want to sort of go through that. So we have symbols in K0, K1, and K2, which we can write down. So I think I mentioned that in K0, in particular, we have the point 1, 1 on GM squared, and that gives you a copy of Z. And we take 1 in this copy of Z, and we call that E. So that's an element of K0. That's the symbol in K0 that we're interested in. In K1, we need a whole bunch of symbols. So take any pair of integers which are relatively prime. And we'll define angle brackets AC to be 1 minus Z1 to the B, Z2 to the D in the sort of which is a unit on the rank 1 torus given by the kernel of the map that takes x comma y to ax plus cy. So this is sort of a rank 1 torus in terms of this rank 2 torus here. What are B and D? Well, B and D are chosen to, so you get a matrix in SL2Z, AD minus BC is 1. Choose them to be anything, it's independent of the choice, because we're only considering 1 minus Z1 to the B, Z2 to the D as a unit on this torus. Of course, it's not a unit at 1, so we have to remove 1. It has a 0 there. And you'll notice that the way I've constructed things, this AC is the pullback by the matrix ABCD of the symbol sort of 1, 0. Okay, so that's our symbol in K1. We have those symbols in K1. And in K2, I take a matrix now not in SL2Z, but in GL2Z, but I'll almost always call it ABCD and gamma. And the symbol corresponding to gamma is, which I'll also write as this sort of AC pair BD, is the cup product of 1 minus Z1 to the A, Z2 to the C, and 1 minus Z1 to the B, Z2 to the D. And where does that lie? It lies in H2 of GM squared minus the 2 tori that we used in defining K1, right? SAC and SBD with twist is 2. And the way we define this gamma, the symbol corresponding to gamma is the pullback by gamma of the symbol of the identity matrix. Okay, so I guess one thing we'd want to know is what are the residues of our symbols? And the residue of the symbol AC is just this E, independent of A and C, okay? And the residue of the symbol gamma depends on whether it determines 1 or minus 1. If it's 1, it's the symbol AC minus the symbol minus B minus D. So there's a bit of a sign issue, but this is quite easy. So what are these residues? The residue, the first one measures the zeros or poles, okay? So here AC has a 0 at 1, a simple 0, so that's why you get E. And the other one is the tame symbol in K-theory. Okay, so if you just compute the tame symbol of this cup product, or the Steinberg symbol, then you get this. Okay, so it's a very simple computation. Right, so you're sort of computing, for instance, 1 on, on where the other one vanishes. Okay, so that's why you return these symbols. Okay, so now here's the proposition. Let's let K2 bar be the quotient of K2 by H2 GM squared 2. There's a unique 1 cocycle on GL2Z valued in this K2 bar, characterized by the property that the residue of theta of gamma, which I'll write theta sub gamma, is gamma star minus 1 of the symbol 0, 1. Okay, so this proof is rather easy. If I have 2 matrices in GL2Z, I take the residue of theta of gamma mu, that is gamma mu star minus 1 of 0, 1, and then I just break that as a sum of 2 things, gamma star minus 1 of 0, 1, and gamma star of mu star minus 1, 0, 1, which of course is the residue of theta of gamma plus gamma star of the residue of theta of mu, because we have a GL2Z equivariant complex. And now, because I've quotiented out by H2 GM squared 2, the induced map by the residue is injective. So we have the cocycle condition, right? I mean, it's already true. It's true for residues, right? That it's a so it's true for theta. Okay. So that's the whole proof. So now we know there exists a cocycle, great. But what can we say about it? Okay, well, one thing you can say is it's parabolic. And the way you check this is simply that you look again at residues and you check that the residue vanishes on this. So by parabolic, The parabolic condition might be a little bit strange, but this is the sort of parabolic subgroup we want to look at. You can see that theta vanishes identically on this parabolic subgroup, and all others that we're interested in are conjugates of this one. And so therefore it will be a co-boundary on all of those from usual properties of cohomology. So it's quite quick to prove it, to check it's parabolic. You just check it vanishes on one parabolic subgroup. More interestingly, it satisfies an explicit formula. So how do we do this? Okay, if you have a matrix in GL2Z, I'll define a connecting sequence for this matrix to be a sequence of pairs in Z squared, such that, let's say from 0 to k, Vi from 0 to k, where V0 is 0, 1, and Vk is the BD up to the sign, which is the determinant of gamma. And we choose these so that the determinant of sort of each matrix you get from consecutive pairs, as written here, is 1. We can do this by the Euclidean algorithm, right? The usual, or continued fraction expansion, or whatever you want. So if I have gamma in GL2Z and I have a connecting sequence for gamma, then I have the following explicit formula for theta gamma. It is the sum of the symbols Vi, comma, minus Vi minus 1 in this K2 bar. And the proof, again, is just by computing residues. We take the residue of the sum on the right by what I said about the symbols. So I've now written so the symbol here means the symbol of the matrix where the first column is Vi and the second column is minus Vi minus 1. Okay, so now I gave you a formula for the residue of this already. So that's just the difference of Vi, the symbol for Vi, where that's the symbol of the pair, and the symbol of Vi minus 1. The sign sort of corrects itself here. There was a sign in the residue, and there's also a sign, okay, which is now corrected. And then it telescopes, you end up with the first term and the last term. The first term is gamma star of 0, 1. That gives you the symbol Vk. And so you get the residue of theta of gamma. And since the residues agree, the elements were equal in the first place. Okay, so that's the entire proof. Now, slightly more complicated is Hecke equivariance. Let me just mention what our Hecke operators are. Because we have this right action, they sort of differ a little bit from the usual Hecke operators. So we do a coset decomposition as follows, I guess. And so we have, I guess in our, I guess I've written here in the particular case, so gamma is GL2Z, and I take the matrix I'm interested in, which would be 1L. Then we write it like this. Okay, yeah, it's sort of the usual thing, but the TL of theta of gamma, here we have, the point is gamma of GJ is going to be G of some sigma J, where sigma is some permutation of 0, L times some gamma J in gamma. And then we have this formula for Hecke operators as the sum of pullbacks by G of sigma J, theta of gamma J. And this is sort of depends upon the choices I make in the coset decomposition, but somehow only up to co-boundary. So, but in order to say I'm acting on cocycles, I'm going to take these particular representatives that I've written down. Let me just check one thing. Sorry. Yeah, I was worried about that. I wrote down this is a typo. Okay, so actually, it's L1, okay, not, Oh, somehow I lost my screen. Oh boy. Did everybody lose the screen?
Yes, we lost the screen, yeah.
Okay, let me get it back.
Yeah.
Okay, yeah. I was checking to see that this was a typo. Yeah, so actually G0 is L1 and GJ is LJ1. Okay, I correct that. Okay, so anyway, that's a little different than what's standard. Okay, so that gives you the Elf-Hecke operator on cocycles. And I will take this particular choice of coset. Maybe I can actually write. I'll take this particular choice of coset representatives. Okay. Okay, so for the Eisenstein property, so this equality is an equality of classes, not of cocycles. Okay, TL of theta is L plus pullback by multiplication by L of theta. And I probably do not have time to go through the proofs, so I'm going to sort of skip that. But let me just point out the key fact which gives it to you. If I imagine TL acts on K by the sum of pullbacks by these operators, then I can have it act on K0. And what does it do to the class E? Okay, so each GJ star applied to E is going to give me some cyclic subgroup of order L in mu L squared. And if I take the sum of all of those, I get pullback by L of E, mu L cross mu L, but I am counting the identity actually gets counted for all L plus 1 subgroups. So I have L more copies of E. So it's L plus diamond operator, or plus pullback by L E. And that is the sort of key fact which gives you Hecke equivariance for all TL. Or I mean, the Eisenstein property. So I'll call this the Eisenstein property of theta. Okay. So I guess I have this brief interlude here of a different way to think of this theta. If you imagine that we defined sort of equivariant motivic cohomology as the hypercohomology of sort of group cohomology acting on Bloch's cycle complex, for instance, or any complex that computes motivic cohomology, then automatically, so I put a sub gamma for equivariant cohomology, automatically, just by its definition, it'll come endowed with a spectral sequence with group cohomology of motivic cohomology converging to this equivariant motivic cohomology. And so if, so let me invert 6 in this description. If I do that, then somehow I'll also have Giesen sequences, I believe, and I look at H3, equivariant H3 for GM squared minus 1. The Giesen sequence will take that isomorphically to H0 equivariant motivic cohomology for the class of 1, 1, which is also just a copy of Z. So we've inverted 6. So I take 1 in there and I pull it back. That gives me a class in this equivariant H3, which I'll call E. And now I pull this back to Q of GM squared and use the spectral sequence to map it to H1 gamma H2 Q GM squared 2. So now I have a GL2Z, so gamma is GL2Z here. I now have a GL2Z cocycle valued in the group I had before. In fact, something slightly better, but remember I've inverted 6. And I believe that this should be the class of theta. And so we have a remark similar to this in the paper. It's a slightly different version. So in fact, if you just want existence and you're willing to invert some primes, you have this pretty powerful way of doing this sort of thing. Okay, so now let me talk about specialization. So the ambiguity coming from H2 GM squared 2 is a little too large, so I want to cut it down some. So for that, I look at trace maps. So we have these maps, we have multiplication by integers on our cohomology group, so we can, or on, we can push, sorry, on our group scheme, so we can push forward by that. And somehow that defines trace maps on our complex K, which are sort of sums of norm maps for field extensions, where sort of my is x. And I want to look at traced fixed parts. So traced fixed parts I'll denote with an upper 0. These are the parts where all m star fix your element, okay, for all m greater than or equal to 1. So let me give you an example of how this m star works. If I have 1 minus z in q of gm, let's just take gm instead of gm squared. Z is the coordinate function. M star takes 1 minus z. It sort of first pulls, yeah, right. Sort of first takes z to z1 over m, and then it takes the product I equals 0 to m, 1 minus zeta m to the I, z to the 1 over m, which is 1 minus z. So it fixes 1 minus z. So in fact, what turns out to be the case is that all of the symbols I defined are all trace fixed. So we're already working in trace fixed part, which is quite nice. And so what is the trace fixed part of H2 GM squared 2? It's actually also quite simple. It's just the subgroup generated by the cup product of minus z1 and minus z2, where z1 and z2 are the two coordinate functions on GM squared. So that's a copy of z. And so we can reduce, in fact, because our symbols are all trace fixed, we're able to reduce the ambiguity to this trace fixed part. So a copy of z for theta. We can actually do a little better than that if we are willing to invert 6, as I sort of alluded to before. Right, so now that's going to help us when we specialize. So how are we going to specialize? As I was mentioning much earlier, we have a torsion point on the q mu n points of GM squared, which is 1 comma a primitive nth root of unity zeta n. So we have a specialization map, so pullback by, right, which is for this, which is somehow given on coordinate rings by taking sort of z1 to 1 and z2 to zeta n. So pullback by this S takes the cup product of minus z1 and minus z2 to the Steinberg symbol minus 1 comma, that should be a minus zeta n. And that'll be minus 1 if n is odd, and 0 if n is even. Okay. I'll fix that later. Okay, but there's an issue that the pullback by this S makes no sense on K2. There's no morphism from Q of GM squared to Q mu n, right? But if we work with a slightly smaller group, this K2 actually contains all the motivic H2 they inject in there with 2 coefficients of open subschemes of GM squared. So I can choose an open subscheme. I just work with open subschemes which contain 1 comma zeta n, so I can pull back, and I take sort of direct limit of all these H2s over these open subschemes. That's a subgroup of K2, and if I land in this subgroup, then I can pull back. Unfortunately, well, I mean, it has to be this way. On GL2Z, I do not land in this subgroup, but I do on a congruence subgroup of GL2Z. So let's define gamma naught tilde of n to be the matrices in GL2Z such that n divides the lower right left-hand corner. Call that gamma naught for short here. And if I have gamma in gamma naught, then in fact, sort of by its residue, we can see that theta of gamma lies in H2 of gm squared, where I subtract out the two tori 0, 1 and for S01 and SBD. Now, because n divides C, right, for something in gamma naught, it does not divide D. Okay, and because it does not divide D, inside this U, which is this complement, I do have 1 comma zeta n, so I can pull back by it on this congruence subgroup. And so, oh no, I lost it again. I'll get it back. Okay, so so I can pull back as long as gamma is in gamma naught. And the ambiguity is now just in 1 comma minus zeta n. So I get a cocycle on gamma naught valued in K2 of Q mu n modulo the group of order 1 or 2 generated by this symbol. Okay. Let sigma d be the element of Galois, the Galois group of Q mu n over Q, which raises nth root of unity to the dth power. We have a map from gamma naught to this group, which takes matrix to sigma of its lower right-hand corner. And then we can let gamma naught act on K2 via that map. In fact, delta will act on K2. Delta naught, I guess, similarly defined, will act via that map. And here's then the theorem. This specialized cocycle is parabolic. It satisfies the explicit formula, which comes from specializing the explicit formula I had before. Theta and gamma is a sum of Steinberg symbols of cyclotomic n units as follows. So we have a connecting sequence, but now we only care about the second term in it. But here I have to choose the connecting sequence. So this makes sense, so that n doesn't divide any of the di's. So I call that an n connecting sequence, and that can actually be done if your matrix is in gamma naught of n, or gamma tilde naught of n. Now the Eisenstein condition passes through because the coset representatives remain the same as long as L is prime to n. And that's sort of the key reason this works just for L prime to n. There's one tricky point in the fact that I sort of switched when I changed the ambiguity, I may have lost a bit of control over the class. So for T2, we have to multiply by 2. I don't think that that's real probably, but it goes away later, so that's fine. Theta n, actually, in fact, you can see here, it takes values in K2 of Z mu n with n inverted because these are Steinberg symbols of n units. In fact, it takes values in K2 of Z mu n, which is a subgroup, which is less obvious, but that's true. Right, so all these properties follow from what we've already shown for theta. Okay, so now how does this give us maps on homology? Well, the point is that on gamma 1, which is the things in gamma naught where D is 1 mod n, this becomes a homomorphism because the action on K2 was through the sigma D. It's also a parabolic cocycle. So when I restrict it to gamma 1, or gamma 1 of n, the usual gamma 1 of n for SL2Z, I get a homomorphism on the cohomology of Y1n. Because it's parabolic, it factors through X1n, and because it was actually defined on this sort of gamma 1 for GL2Z, it factors through the quotient by complex conjugation, where complex conjugation acts trivially. So I get a homomorphism like this, which is slightly better than what we had. But now if I invert 2, the ambiguity goes away, and I get the map I claimed we had in the beginning. And you can check via the explicit formulas that this agrees with the map, which is the restriction of the map, which takes a Monin symbol to cup product of cyclotomic units, as the explicit formula might have indicated. We actually don't define pi n circ, which is the larger map on homology relative to the cusps. I'm not sure. Yeah, it might be possible to do this, but we haven't done it. So that involves sort of constructing a partially compactly supported cocycle. The map is Z mod NZ cross equivariant, sort of by definition. And now I should point out that this condition, so our theorem here on the previous slide was that TL minus L minus sigma L kills theta n, which translates, because of the equivariance, to TL minus L minus diamond operator L kills pi of n. But that appears to be the wrong condition. And somehow the point was that, and I guess I didn't say this, the way I originally defined the map was such that we didn't take the usual Monin symbol, but we took the Monin symbol and applied an Atkin-Lehner involution for n to it. So that switches the role of usual and adjoint operators. And when you switch that role, that switches the one sort of Eisenstein series to the other. So here I've taken sort of usual Monin symbols, if you like, in defining pi n. So it's not quite the same map, and so it's not quite the same Eisenstein condition. But the conjecture would also be that it's Eisenstein then, if I'm writing it this way, for the operators UL star minus 1, not UL minus L, that it would be Eisenstein for UL star minus 1. Okay. Right. Where UL star is the dual correspondence. Okay, so in the few minutes, I'll try to say very quickly, maybe I'll have to skip some things, indicate something about the elliptic curve squared case. So we have, again, by the same reasoning, if we take an elliptic curve squared over a base scheme over a characteristic zero field, in general, we'll have a complex like this. Again, it will compute the 4 minus ith cohomology of E squared, because that was a sort of a general fact. Here, though, the problem is that none of those groups vanish. So you know, the homology is not just in the first degree. I mean, it's everywhere. And so in degree 2, it's everywhere. So what we do is, off the bat, we take trace fixed parts. And it turns out that if you take trace fixed parts of these cohomology groups of E squared, then they vanish except for H4. So somehow the homology would be in the final degree. Now here, I'm actually going to redefine trace fixed parts to be trace fixed parts for all m prime to some fixed integer n. I don't need that for E squared, but I do need it for the construction. And here, to take trace fixed parts, I actually need to invert an integer first. I think we can get away with inverting 6. And then what I said is true. And the proof involves sort of for a Mukai transform Motivic decomposition of the diagonal due to Denninger and Mur, but we have to slightly improve that just to deal with coefficients they deal over coefficients in Q. And we just have to figure out what we can invert and not. Okay, but now the problem is taking a trace fixed part is not exact. So even though you get a complex like this, it's not quite exact necessarily at K naught. But let's suppose I had something in, so I think of this map from K naught to Z prime as like a degree map. K naught is like sum of codimension 2 cycles. And okay, so I imagine it's like a degree map, which it really is. If I have some, maybe formal sum of torsion points, which is GL2Z fixed and degree 0. And if it happens to be in the image of the map from the trace fixed part of K1, then automatically I'll get a cocycle by the same construction as before. And now where we actually apply this is we take E to be the universal elliptic curve over the modular curve y1 of n, where n say at least 4. And I'll take my class in K0 to be the following awful class, where written here. Okay, what is the key thing about one key thing about this class is that it is the residue of an element in K1, which I call 0, 1, n, which you can define explicitly from theta functions and their divisors. And those in turn, their differences are residues of symbols in K2. Okay, so so if I take the resulting cocycle, which I'll call theta with an n before it, in an analogy with maybe Kato's notation for theta functions. It's parabolic. It satisfies an explicit formula for sums of symbols formed out of exterior products of theta functions. It's equivariant in the following sense. TL of theta n for L not dividing n is, its class is the same as a different TL. So there's two types of operators now. The Hecke operators I defined before, and those coming from correspondences on the modular curve. So we define correspondences, you know, sort of usual ones on the modular curve, coming from, and these give maps of complexes. The complex is K, and so they give maps on cohomology. Right, so group cohomology. So the classes agree, in fact, at least if L doesn't divide n. Now, a difference here is now there's no universal cocycle independent of n. That's sort of like with theta functions, where there's no theta function for n equal 1, right? You need to choose something divisor of degree 0 when you define a theta function. But there's some comparison between the different theta n's you can define via these strange operators. The point of this VL here, which I've written here, is that VL of 0 is the EN I wrote down. And so you can compare the classes of VL of theta n and VN of theta L, and they're the same. Okay. So now we specialize again now by pullback by the torsion section 0, comma, the canonical end torsion section of the universal elliptic curve mapping down to y. That gives us a cocycle to H2y Z prime 2 on gamma naught of n. As before, it's Hecke equivariant for prime to level operators. It does depend upon this n, but now, just as with Siegel units, there actually exists a universal cocycle as long as I invert n. So it's not quite rational, but it exists. And then you can compute an explicit formula for this universal thing. You could have computed it for these and gotten for the ones with the auxiliary prime n and got an exact formula, but somehow you lose the precision, or we lose it, when we try to write down an explicit formula for this universal thing. There's some ambiguity coming from the kernel of all sort of VLs for the correspondences, the common kernel for all of them. But this sort of ambiguity in the explicit formula will vanish in any realization. So here it's as a sum of Steinberg symbols of, or I guess cup products, I should have written it as, of Siegel units. Okay, so the point is that these, this should be theta sub n on the right. It induces a zeta map, and this zeta map is Hecke equivariant for prime to level operators. So this recovers, you know, a construction of Gonchar and Bruneau to K2 of the modular curve, and a construction of Fukaya-Kato on the ordinary part of the tau cohomology of the modular curve. Fukaya-Kato show that their map is Hecke equivariant. they do it for p dividing n. Wang and Le Couturier can do this. I guess they do it for n prime, but it can be done for p naught dividing n, and you don't need ordinary parts. And we can actually also construct sort of an integral version of this as long as we remove a bad eigenspace. Okay, and finally, well, I'm out of time, so maybe I'll just stop there. If you're interested to know, I'll tell you what finally is. Thanks.
Thank you very much, Romyar, for your lecture. There are any questions?
Yeah, actually, I have a question. Can you say something at the very last line? Why do you have to remove omega squared? Does that have to do with some pole of a zeta function or something?
Yeah, I mean, the Ziegler units aren't quite, well, I mean, it's not quite integral there, I guess is the point. Does it have to do with the pole of a zeta function? Well, the Ziegler units aren't quite integral, and then I guess it's a point of figuring out where they're not quite integral. And I think it's the same place, the same eigenspace. Yeah, it's been a while since I thought about the reason for this. We actually came across the same thing. Fukaya-Kato and I had proved sort of there's an integral version of this as well on primitive eigenspaces, and we also had to remove the omega squared eigenspace. And so we're doing the same thing here. Yeah, I mean, I think it's just where you look at the integrality of the Ziegler units. So
yeah, I'm wondering if you
same eigenspace.
get around that by imposing some auxiliary level structure.
Auxiliary what? Like an n or something? Little n?
Yeah, like introducing another prime and.
Yeah, well, I mean, so yeah, so I guess the point is that if I define a zeta map nzn from my cocycle n theta n, then I will get something integral. I don't need to worry about integrality. It's already integral. But if I want to define this sort of universal thing, then it won't be integral in general. I guess what Fukaya and Kato do is they actually measure how big the denominators are. But I guess it's a similar thing. We could do that too. If I multiply by a certain operator, then this thing will be integral because I'll get the n, the zeta map that depends upon this auxiliary prime n. That is like introducing an auxiliary level structure,
yes.
Sort of a gamma naught little n level structure.
Yeah.
Yeah.
Are there any other questions or comments for Romyar?
I may have one. Yeah.
Mm-hmm.
Yeah. So you in the GM square case, the map you get is for absolute homology, right? But because you restrict to gamma 1n, but you get something for gamma 0n, right? Which is not a group homomorphism, but just a cocycle, and I believe it should give you the relative homology with the non-infinity cost.
The thing for gamma naught should give the relative homology?
Yeah, I believe so. It seems and go into K2 of Z zeta n 1 over n instead of K2 Z zeta n.
Well, I mean, it does go to K2's, Z1 over n. It does not land in, that's right. Oh, so you're, so
just
the fact that it's a cocycle.
Free, I believe so.
Well, okay, so maybe that'd be interesting to hear. Okay, maybe you could explain to me why that is. Yeah. Oh, maybe because, okay, yeah.
So I have a small question. I mean, what kind of Hecker module is this H1 of x1 of n with values in the K2? I mean, so you're considering these explicit elements in this module, but what do you know about what the
Sorry, could you say that again? Sorry.
The H1 of modular curve or of gamma 1 of n with value K2, either of the cyclotomic field or of the cyclotomic ring or the modular curve. What is it as a Hecker module? Is it like very big? Do we have any sense of what it looks like in terms of the spectrum of the Hecker operators acting on them?
H1 of the K2, you said?
H1 of a group with values in the K2.
Group cohomology.
Yeah, for example, right, exactly. So where your elements live, right? I mean, these elements that you're constructing.
Right. Well, I mean, I guess. Oh, you mean is it very big? I mean, of course, the Hecker algebra actually acts. So I mean, So you know that. I guess. I mean, I guess when you're looking at the coefficients in the modular curve, then you expect it to be quite large, right? But but if for K2 of you mean like K2 of z mu n or something like that? What is?
For example, right? So these two things that you're considering, the H1 resides in K2 of z mu n or in K2 of the modular function field.
Well, I mean, I don't see automatically why it's any so smaller than sort of the usual Hecker algebra for weight 2 form, for gamma 1 of n.
I see. It couldn't be. So is that your intuition is that it's roughly that you can diagonalize the Hecker operators acting on that space, and that you'll pick up eigenvalues attached to modular form. It's not something like functions of the modular curve, which would have no Hecker stable subspaces of finite dimension, that kind of thing. I mean, it's when you go to K2 is very poor, so I really don't know what to expect.
Yeah. Well, I mean, K2 is quite a small group in the case of z mu n, so I mean, it could be quite small. I mean, it's not going to be the full thing in general. But I don't know, why it would be restricted in that way. Yeah.
And for the case of the K2 of the modular function field, this is an element that you construct. You could imagine decomposing it in terms of isotypic components for the Hecker algebra. Is that something that's interesting to do, or is that sort of an unreasonable thing to?
The H1 of the
this element made from elements in K2 of the with the Siegel units, right?
I mean, sure, that's something you could do. Yeah, that's a reasonable thing to do. I mean, at some point we look at ordinary parts, right? So that's also kind of partially decomposing it in that way.
Okay.
Yeah.
And if you do that, do you get some information about L values? Is that sort of what you get? You get like coefficients that tell you about sort of ranking functions or something?
You mean if you like take a regulator or something like this? Yeah, I mean, I guess it tells you about L values of your cusp forms. Yeah. We don't actually compute any. Oh, I lost it. We don't actually compute any regulators in what we do. That's part of the nice thing about the approach, right? We don't have to compute any regulators. That's true. So I guess. Right. The one thing I didn't say is, there's a lot of other cases that you could use maybe this method to study. And we sort of focused on the two cases which were sort of related to my sort of original conjecture, but it's quite clear you get a lot of other cocycles pretty quickly, and then you have to kind of study them in depth.
So there's a Hilbert modular surface story in particular.
Yeah, you could, but at least you could get elements like zero cocycles. valued in K2. Yeah.
Are there any other questions for Romyar or remarks? Okay, so I think this is a good time to close the morning session. I want to thank again Romyar for his very interesting lecture. Another round of applause. So for